Let me tell you something that's going to sound absolutely crazy. Something that contradicts what you learned in school, what you've read in every popular science book, what you've heard from every science documentary narrator. The Big Bang never happened. There was no beginning, no moment of creation, no singularity 13.8 billion years ago where the entire universe exploded into existence from a point of infinite density. Now, before you close this video thinking I've completely lost my mind, let me be very, very clear about what I'm saying. I'm not denying the Big Bang Theory. I'm not saying the universe isn't expanding. I'm not saying the cosmic microwave background doesn't exist or that we can't trace the universe back to a hot, dense state 13.8 billion years ago. What I'm saying is that the picture of the Big Bang as a moment of creation, as a singularity where everything began, is almost certainly wrong. It's an artifact of pushing general relativity into a regime where it simply doesn't apply. And when you actually apply the right physics, quantum mechanics, quantum gravity, whatever the correct theory turns out to be, the singularity disappears. The beginning disappears. I've been working on the fundamental problems of cosmology and quantum gravity for my entire career, and I can tell you the idea that the universe began in a singularity is almost certainly false. Let's start with what we know. What does the Big Bang Theory actually say? The Big Bang Theory says that the universe is expanding. Galaxies are moving away from each other. Space itself is getting bigger. And if you run this expansion backward in time, if you play the movie in reverse, you find that the universe was smaller in the past, denser in the past, hotter in the past. 13.8 billion years ago, the entire observable universe was compressed into a region smaller than an atom. The temperature was trillions of degrees. The density was incomprehensibly high. This is what we call the early universe, the hot Big Bang phase. And we have extraordinary evidence for this. The cosmic microwave background, the faint glow of radiation that fills all of space, is the afterglow of this hot, dense phase. It's a snapshot of the universe when it was only 380,000 years old, cooling from trillions of degrees to a few thousand degrees. And the patterns in that radiation match the predictions of the Big Bang Theory with stunning precision. So the Big Bang Theory works. It's one of the most successful scientific theories ever developed. But it has a problem, a deep fundamental problem that physicists have known about for decades. If you keep running the expansion backward, if you keep extrapolating to earlier and earlier times, eventually you reach a point where the density becomes infinite, the temperature becomes infinite, the curvature of space-time becomes infinite. General relativity predicts a singularity, a moment equal to zero, where the laws of physics break down completely. And this is not some minor technical detail. This is general relativity telling us, in the loudest possible terms, that it doesn't work at t equals z. The equations blow up. They give nonsensical infinite answers. The theory is breaking down. Now, some people hear singularity and they think that's just what the Big Bang is. The universe began in a singularity. That's the creation event. That's where it all started. But that's not what a singularity is. A singularity is not a physical thing. It's a mathematical breakdown. It's a theory waving a white flag and saying, I don't know what happens here. You need better physics. Think about it this way. Imagine you're using Newtonian physics to describe the motion of a baseball. You throw the ball and Newton's laws tell you exactly where it goes. But then you decide to calculate what happens if you keep accelerating the baseball faster and faster, approaching the speed of light. Newton's equations start giving you nonsensical answers. The mass of the baseball becomes infinite. The energy becomes infinite. Does that mean there's a singularity when the baseball reaches the speed of light? No. It means Newtonian physics doesn't work at those speeds. You need special relativity. The Big Bang singularity is the same thing. General relativity doesn't work at the extreme densities and temperatures of the very early universe. You need quantum mechanics, you need quantum gravity. And when you include quantum effects, the singularity goes away. This has been known, at least in principle, for decades. Roger Penrose and Stephen Hawking proved in the 1960s that general relativity inevitably predicts singularities in black holes and at the Big Bang. But they also understood that these singularities were signals that the theory was incomplete. Hawking himself said repeatedly that the singularity is not real. It's a breakdown of the classical description. Quantum effects, whatever they are, must smooth it out, eliminate it, replace it with something else. So what happens instead? What replaces the singularity? The honest answer is we don't know for sure because we don't have a complete theory of quantum gravity. We have candidate string theory, loop quantum gravity, various other approaches, but we don't have the final answer. However, we can make some educated guesses based on what we do know about quantum mechanics. In quantum mechanics, there's a fundamental limit to how small things can be. You can't localize a particle to a region smaller than its Compton wavelength. You can't squeeze space and time arbitrarily. Quantum fluctuations, the uncertainty principle, put a fundamental limit on how compact things can get. This suggests that when the universe was very, very small, smaller than the Planck length, about 10⁻⁻35 meters, quantum effects dominated. Space-time itself became quantum. The classical concepts of space and time broke down, and instead of a singularity, you had something else, a quantum state, a wave function of the universe. One proposal, which I find quite elegant, is called loop quantum cosmology. This is an approach based on loop quantum gravity, which tries to quantize space-time itself. In loop quantum cosmology, the Big Bang singularity is replaced by a big bounce. The idea is that before our expanding universe, there was a contracting universe. It collapsed down to an incredibly small size, but not zero, not a singularity. Quantum effects created a kind of repulsive force that prevented complete collapse. At the smallest scale, gravity became repulsive rather than attractive. The universe bounced. It transitioned from contraction to expansion. From our perspective, looking backward in time, we see the universe expanding from a very small, very hot state. That's the Big Bang. But if we could look before that, if the concept of before even makes sense, we'd see a previous universe collapsing into the bounce. Is this the right answer? Maybe, maybe not. Loop quantum cosmology is still a work in progress. There are technical issues that need to be resolved, but the basic idea that quantum effects eliminate the singularity is almost certainly correct. Another proposal, which doesn't require a bounce, comes from the Hartle-Hawking no-boundary proposal. This is an idea that Stephen Hawking and James Hartle developed in the 1980s. The basic idea is subtle and beautiful. They proposed that in the very early universe, time itself was different from what we experience now. In quantum gravity, at the Planck scale, time can become what's called imaginary. Not imaginary in the sense of not being real, but imaginary in the mathematical sense involving the square root of -1. When time is imaginary, it behaves like a spatial dimension. And in this regime, the question, what happened before the Big Bang, becomes meaningless, like asking, what's north of the North Pole? There's no before. Time just curves around and closes off smoothly. No boundary, no beginning, no singularity. Again, this is speculative. The mathematics is subtle, and not everyone agrees on how to interpret it. But it's another example of how quantum effects eliminate the singularity and make the concept of a beginning problematic. Now, let me tell you about something that makes the whole question of the Big Bang even more complicated, even more strange. It's called eternal inflation, and it's one of the most profound ideas in modern cosmology. Inflation is a theory proposed by Alan Guth in 1980. Actually, around the same time, similar ideas were being developed by André Linde and others. The basic idea is that in the very early universe, there was a brief period of incredibly rapid expansion. In a tiny fraction of a second, the universe expanded by an enormous factor, maybe 10 to the 60th or even more. This inflationary expansion solved several problems with the standard Big Bang model. It explained why the universe is so flat, so uniform, so homogeneous on large scales, and it predicted the tiny fluctuations, the seeds of galaxy formation that we observe in the cosmic microwave background. But here's the thing. Almost all models of inflation don't just inflate once and stop. They inflate forever, or more precisely, inflation becomes eternal. Here's how it works. Inflation is driven by a hypothetical field called the inflaton. When this field is in a certain state, a false vacuum, it drives exponential expansion. Eventually, the inflaton decays into ordinary matter and radiation. Inflation ends. You get a big bang, a hot, expanding universe filled with particles. But here's the key point. The inflaton field is subject to quantum fluctuations. In some regions of space, these fluctuations can kick the inflaton back up to the false vacuum state. And when that happens, inflation starts again. That region inflates exponentially, creating new space. And within that new space, more quantum fluctuations create more regions of inflation. The result is a fractal structure, a never-ending branching tree of inflating regions. Some regions stop inflating and become pocket universes, regions like our observable universe. But the inflating regions keep producing more inflating regions forever. This is eternal inflation, and it has a profound implication. There is no beginning, or rather there's no global beginning. Individual pocket universes like ours have a beginning. Our Big Bang happened 13.8 billion years ago. But the larger structure, the eternally inflating multiverse, has been inflating forever. It has no beginning in time. Now there's a theorem, the Borden theorem or BGV theorem, that says that even in eternal inflation, you can't have inflation going infinitely far into the past. If the universe is expanding on average, you can't trace it back forever. There must be a boundary. But that boundary is not a singularity. It's not a moment of creation. It's more like an edge, a place where the classical description breaks down and you need quantum gravity. And beyond that edge or before that edge, if the concept of before makes sense, we simply don't know what's there. Quantum cosmology, a wave function, a quantum state of the multiverse, something. Let me tell you why I think this picture, eternal inflation, no beginning quantum cosmology, is probably the right one. First, it's generic. Almost every model of inflation that we can write down leads to eternal inflation. You have to fine-tune the parameters very carefully to get inflation that doesn't become eternal. And in physics, when you have to fine-tune to avoid something, that usually means nature doesn't fine-tune. Nature goes with the generic case. Second, it fits with what we're learning from string theory. In string theory, there's what I've called the string landscape. An enormous number of possible vacuum states, perhaps 10 to the 500 or more. Each vacuum state corresponds to a different set of physical laws, different particles, different constants of nature. In eternal inflation, all of these vacuum states get realized somewhere in the multiverse. Quantum fluctuations during inflation explore the landscape. Some regions decay into one vacuum, some into another. The result is an infinite multiverse with infinite diversity. Our observable universe is just one pocket, one bubble in this vast structure. We live in a region with the particular laws of physics that we observe because, well, we couldn't exist in most of the other regions. This is the anthropic principle, and while it makes some physicists uncomfortable, I think it's probably the right way to think about the universe. Third, the picture of an eternal, beginningless multiverse resolves some deep philosophical problems. The problem of initial conditions. For instance, in the standard Big Bang picture, you have to specify the initial state of the universe. What was the density? What was the temperature? What were the quantum fluctuations? These are all fine-tuned to incredible precision to produce a universe like ours. Why that particular initial state? The Big Bang theory doesn't answer that question. But in eternal inflation, there are no initial conditions. Or rather, the initial conditions don't matter. Whatever the multiverse started from, if it even makes sense to talk about it, starting eternal inflation washes out the memory of those initial conditions. Every possible state gets produced somewhere, and we find ourselves in one that's compatible with our existence. Now, I want to address something directly, because I know what you're thinking. You're thinking, Lenny, this all sounds like untestable speculation, multiverse, eternal inflation, quantum cosmology. How can you possibly test any of this? And that's a fair question. We can't directly observe other pocket universes. We can't probe the Planck scale to see quantum gravity in action. We can't watch the Big Bounce or measure imaginary time. But we can test the framework indirectly. Inflation makes predictions about the cosmic microwave background, about the spectrum of fluctuations, about gravitational waves, about the geometry of space. And so far the predictions match the observations remarkably well. Loop quantum cosmology makes predictions about how the bounce affects the structure of the early universe. These might be testable with future observations of the CMBB or of primordial gravitational waves. The string landscape and eternal inflation make statistical predictions about what kinds of universes should be common and what kinds should be rare. These are harder to test, but they're not untestable in principle. And most importantly, the alternative, the idea that the universe began in a singularity with infinities and a breakdown of physics, is definitely wrong. We know it's wrong because the theory that predicts it tells us it's wrong. So we're not choosing between a testable theory and an untestable one. We're choosing between a theory that definitely breaks down and a framework that might be correct, but is harder to test completely. Let me tell you a story. When I was younger working on black hole thermodynamics and the information paradox, a lot of physicists thought I was wasting my time. Black holes, information thermodynamics, these were abstract theoretical questions, not real physics. But we kept working on them because the theory demanded it. Quantum mechanics said information can't be destroyed. General relativity said it is destroyed in black holes. Something had to give. And over decades of work, my work, Hawking's work, Tufts' work, Maldaceno's work, many others, we figured out that general relativity was the thing that gave black holes aren't what general relativity says they are. They're more subtle, more quantum, more informationational. The Big Bang is the same thing. General relativity says there's a singularity. Quantum mechanics says there isn't. Something has to give. And I'm confident that it's general relativity that gives the singularity as an illusion, an artifact, a sign that we're using the wrong theory. The real universe, the actual physical universe, doesn't have a beginning in the way we usually think about it. There's no moment of creation, no first instant of time, just an eternal quantum multiverse structure that has always existed and always will exist, producing pocket universes like ours through the process of eternal inflation. Now, does this mean the universe is infinitely old? Not exactly. Time itself is emergent. It's a feature of the classical low-energy description. At the Planck scale in the quantum gravity regime, the concept of time might not even make sense. So asking how old is the multiverse is like asking what time is it at the North Pole. The question assumes a concept time or unique time coordinate that breaks down in the regime you're asking about. What we can say is this. Our pocket universe, our observable universe, has an age 13.8 billion years. ARs, that's well defined, that's measurable. But the larger structure, the thing that produced our pocket universe through eternal inflation, doesn't have an age in the same sense. It's timeless, or eternal, or beyond time, depending on how you want to phrase it. Let me come back to something fundamental because I think this is where a lot of confusion arises. When we say the Big Bang, what do we mean? If we mean the hot, dense, expanding state that the universe was in 13.8 billion years ago, then yes, the Big Bang happened. Absolutely, no question. We have overwhelming evidence for it. But if we mean a moment of creation, a singularity, a beginning of time, a first instant when the universe came into existence from nothing, then no. That almost certainly didn't happen. That's a misunderstanding, an artifact of taking general relativity too seriously in a regime where it doesn't apply. The Big Bang, properly understood, is not a beginning. It's a transition, a phase change, a moment when our pocket universe transitioned from the inflationary phase to the hot, expanding phase. Before that transition, if before is the right word, there was the inflating false vacuum. And before that, quantum cosmology, the wave function of the universe, something beyond our current understanding. When I lecture to students about cosmology, I always tell them, be very careful about the word before. Before the Big Bang is a dangerous phrase. It smuggles in assumptions that might not be valid. In general relativity, time is part of spacetime. It's not an external parameter. So when spacetime itself is quantum, when the geometry is fluctuating, when you're in the Planck regime, the company, incept of time ordering of before and after might not be well defined. It's like asking what's north of the North Pole. The question assumes that the concept of north applies everywhere, but at the North Pole, north is undefined. Every direction is south. Similarly, before the Big Bang might be undefined, not because there's a wall or a boundary or a moment of creation, but because the framework of time itself breaks down. This is deeply strange. I know it violates all our intuitions. We're used to time flowing smoothly from past to future. We're used to thinking of causality, of events happening in sequence, the idea that time itself might be emergent, that it might not exist at the most fundamental level, that's hard to wrap your head around. But that's what the physics seems to be telling us. And I've learned over 50 years of doing physics that when the mathematics tells you something strange, you should pay attention. Nature is under no obligation to conform to our intuitions. Let me wrap this up by coming back to the title, Why the Big Bang Never Happened. It's a provocative title, and it's meant to be because the conventional picture, the picture that most people have in their minds of the Big Bang as a moment of creation, as the beginning of everything, as a singularity where the universe exploded into existence from nothing. That picture is wrong. The universe didn't begin. It didn't come from nothing. There was no first moment of time. The Big Bang as a singularity never happened. What did happen is that our observable universe, our pocket universe, underwent the transition from an inflationary phase to a hot, dense, expanding phase about 13.8 billion years ago. That transition is what we call the Big Bang. And it's real. It's measurable. It's one of the most important events in the history of our universe. But it's not a beginning. It's just one event in a much larger story, a story that might not have a beginning at all, a story that might be eternal, timeless, fundamentally quantum in ways we're only beginning to understand. This is where cosmology is heading, toward a picture of an eternal multiverse with eternal inflation, producing an infinite number of pocket universes, each with its own Big Bang but no global beginning. Toward a quantum description of the universe, where time itself is emergent and the concept of a first moment doesn't make sense. It's a strange picture. It's a counterintuitive picture, but it's a picture that's forced on us by the mathematics, by the physics, by the deep structure of quantum mechanics and general relativity. The Big Bang never happened, not in the way you think it did. And understanding why is one of the great intellectual achievements of modern physics. Thank you for listening. The universe is stranger than you imagine.